myself Dr. Vivek Jain, Assistant Professor, Biyani Group of Colleges, and today's I am presenting here the Fraunhofer diffraction due to single slit experiment. As we know, the Fraunhofer diffraction occurs when the distance of the source and the screen will be infinite. So here the distance will be infinite, so we use the lens L1 and L2 to focus the diffraction pattern. Okay, so first we see the experimental arrangement. This is the single slit source, this is the source in which the xy is a cylindrical wavefront converted through lens L1 in a plane wavefront. W and W dash is the plane wavefront, and this will be the slit from where the diffraction pattern observed. From the diffraction pattern, the lambda will be the size of the slits. This is the criteria for diffraction pattern. Okay, so this is the incident wavelength with the spherical or cylindrical wavefront converted in plane wavefront by the lens L1. This plane wavefront incident on the slit which have the width A. Now this will be diffracted through an angle theta, here the angle theta, and meet at the point P1. Okay. If theta equal to 0, we get the spots of the source at the point P, which is known as central maxima. To find the intensity at the point P1, we calculate the here part difference, and according to we find the intensity. So to calculate part difference, we draw a perpendicular here. This will be the perpendicular. Now this angle will be theta, so this angle will be theta. Now this width is A, these two lines are parallel, so the part difference will be here, this will be the A sin theta. So part difference equal to A sin theta in the case of single slit experiment. Now if we divide this slit into n parts, so there are two possibilities. If n is a even number, then the diffraction pattern we observed at the screen is known as minimum condition, because these even parts cancel out each other, because the diffraction from the each terms will be lambda by 2. Okay. So first term will be if A sin theta equal to plus minus m lambda, where m equal to 1, 2, 3 and so on. So this will be the condition of minimum intensity for even parts. Second possibility is that if we divide in odd parts, then the even terms will be cancelled out and single term will be remaining. So the part difference will be A sin theta equal to 2m plus 1 minus 1 lambda by 2, where m equal to 1, 2, 3 and so on. So this will be the condition of maxima. So this is the quality wise description of the single slit pattern in the Fraunhofer diffraction due to single slit. Now if we find the how much intensity we get at the diffraction point, so this will be the quantitative description. So this is the phasor diagram, or also known as polygon method. Here we divide the single slit in n terms. The amplitude of each slits will be the amplitude of from this slits will be E0, then it divides in n parts. So the amplitude will be E0 here. The angle subtended from this slit is beta and the radius of this is r, then we can find that angle beta, angle equal to arc upon radius. So angle beta equal to arc will be the E0 and the radius will be the r. So the radius r equal to E0 upon beta. Here we find the radius of this. Now we draw a perpendicular from here. So this angle will be the beta by 2 and this angle again is the beta by 2. So due to trigonometry this will be the r sine beta by 2 and this will be the r sine beta by 2. So the resultant vector for this polynomial is that from this is p and q, then pq equal to 2r sine beta by 2. This is the resultant amplitude. So amplitude will be denoted by A and put the value of R here. So this will be the 2 E0 upon beta sine beta by 2 and we can write it E0 sine beta by 2 divided by beta by 2. If we find the intensity, I is proportional to A square, that is I equal to E naught square sine beta by 2 upon beta by 2 का whole square, that is equal to I equal to I0 sine beta by 2 upon beta by 2 का whole square. Okay. So this is the resultant intensity, where beta will be find as the phase difference, where beta equal to phase difference, which will be calculated by beta equal to 2 pi by lambda into part difference, that is 2 pi by lambda into sine theta. So this is all about the Fraunhofer diffraction due to single slit experiment. First we conclude that due to single slit pattern we find the maxima at the center, and after that we find the minima of different zero intensity. After that we find the intensity of secondary maxima, which will be the decreasing intensity according to the I equal to I0 sine beta by 2 upon beta by 2 का whole square. That's all. Thank you for watching this video, and please like, comment and share the Guru KPO website channel.